Okay, let's recall what we did last time. Last time we talked about the mean value theorem, which is the following. We first talked about the root theorem, which says if a function is continuous on closed interval a to b, and 2, differentiable on open interval a to b, and 3, the two endpoints has the same function value fa equal to fb. The conclusion is there exists number c lies in between this a to b such that the derivative at c vanishes. The geometric meaning of the root theorem says actually is the horizontal tangent line at somewhere. And then we talk about the Lagrange mean value theorem, which is equivalent to root theorem. But actually we remove the condition 3. So no longer have condition 3 is that the two function values at a and b can be different in general. Then the conclusion will be, the first two conditions will be the same. Then the conclusion is the derivative at c equal to the slope of, if we connect the two endpoints, then we get a line PQ. Then the derivative at c actually is equal to the line of PQ, i.e. the slope of a tangent line is the same as the slope of the line PQ, i.e. the tangent line at the point R is actually parallel to the line PQ. And what we did to prove the Lagrange mean value theorem is actually try to transform this problem to root theorem. Such that what we did is we subtract the function by some height function such that the two endpoints at P and Q will have the same function value. So such that we have condition 3. Okay. This is the proof that we did last time. Actually, Lagrange mean value theorem is really important in this course, and it has many important applications. So first of all, this example that we did last time is actually to try to show that a certain equation has exactly one real root. The idea to do this problem is we first show that there exists a root. Okay. What we did is we show that at the two endpoints that the function value is have a negative sign, have opposite sign. At one endpoint it is positive, at the other endpoint it is negative. Then by the intermediate value theorem, there should exist a point x0 such that at x0 the function value is 0. Okay, so this tells us there exists a root. Okay, there exists a root. Now actually we need to do more work to show that exactly one root. Okay, there is exactly one root. What we do is we will show that there will be a contradiction if we assume there are two or more roots. Okay. So what we did is assume that there are two roots. Okay, assume that there are two roots. Then we can apply root theorem. Now you check that the function f(x) is actually satisfies the root theorem, the three conditions of a root theorem. So first of all, how do we construct the function f? Well, if we have an equation, now this equation is actually equal to 0. From this equation, we assume the function, we construct the function f(x) to be the left side subtract the right side. Okay, so here f(x) is defined as left side of the equation, left side subtract the right side. So of course we can use the right side subtract the left side. It's not a big deal. The only difference is we multiply by -1. Okay, then so this kind of problem is routine. First step, try to construct the function f(x) by the left side subtract the right side, okay, of the given equation. Then shows that there exists a root by picking 13 numbers such that you show that the values at the two numbers have different signs, okay, different signs, i.e. one is positive, the other is negative. Then you can conclude that there exists a root, okay, by continuity. Then the next step assumes that there are two roots. Then conclude by root theorem that there's a contradiction. What we did is, by root theorem, if the two function values, they are both 0, so they satisfy condition 3. Now 1 and 2 is automatically satisfied because here we have a polynomial, so it's continuous and differentiable. So by root theorem, we can conclude that there exists a point C such that the derivative at C, 1 is, okay? Now you take a derivative of the function f, and you find it can never be 0. And then you get a contradiction. So you can actually conclude that the function cannot have two real roots. Okay, then you are done. This shows that this has exactly one real root. Okay. Okay, today we will continue some applications of mean value theorems. Okay, first we do this problem. Example. We do this example. Suppose we have a good control about the derivative. Okay, suppose f0 is -3 and f derivative is bounded from above by 5 for all x. How large? Question is how large can the function value f2 possibly be? Okay, now the idea is the derivative tells you how fast that the function increases. Okay, now f derivative is less than 5. This tells us that actually the function increase is at a controlled velocity. Okay, so it cannot be increasing too fast. Okay, now suppose we know f0, the value of f0, then f2 cannot be too large because its velocity is controlled from above. Okay, so here we check that the function we can apply for the function that we can apply mean value theorem. So first of all, now we know f derivative less than 5. This has actually tells us that the derivative exists for every x, So this means fx is differentiable. Okay, so first fx is continuous. It's continuous because it's differentiable. Okay, differentiable implies continuous. Okay, it's continuous on closed interval 0 to 2 because it is differentiable. And differentiable implies continuous. Differentiable everywhere, actually. Differentiable everywhere. So in particular, it's continuous everywhere. So in particular, it's continuous on 0 to 2. Now, second, fx is differentiable on open interval. Differentiable on open interval 0 to 2. Now, because it's differentiable everywhere, in particular, it's differentiable on 0 to 2. 3. So we only need to check 1, 2, okay? Because we only need to use mean value theorem. Okay, by mean value theorem, so then we know that x, we can apply mean value theorem to f. Okay, by mean value theorem. Mean value theorem tells us that f2 subject f0. So the difference of the two function values equal to average velocity i.e. derivative at some c, number c. Now b subtract a, b is 2, a is 0, okay, f0. So this is 2 minus 0, which gives us 2. So this is actually twice, okay, f derivative at c, where c lies in between the open interval 0 to 2, okay. So we want to know some information of f2, so we solve for f2. So f2, we move the terms to the right, okay, f0 we move to the right, so we get f2 is actually f0 plus twice f derivative c. Now f0 is given its value. Now f0 is actually -3 plus twice f derivative c. Remember, f derivative is less than 5. F derivative is less than 5. So this means twice f derivative. So this is computed from above by -3 plus 2 times 5, which is -3 plus 10, which is 7. i.e. we get f2 should be bounded from above by 7. So we have an upper bound. We have an upper bound of f2. So this is the maximum that f2 can be, allowed by mean value theorem. So the largest possible value that does not violate mean value theorem is actually of f2 is 7. Okay, then we're done. Okay, another example. Suppose that 3 is bounded from above by f derivative x, and f derivative x is bounded by 5. i.e. f derivative, the increasing rate of f is controlled from below and controlled from above, so that the function value cannot increase too fast and cannot increase too slow for values x, so that (18) is bounded. So the difference, the function values at 8 and 2, their difference is controlled from above and controlled from below, okay? So the idea is we use mean value theorem. Mean value theorem tells us that the difference of two function values can be obtained by multiplying the average velocity times the change of input. Now we first check actually the mean value theorem applies. So first of all, it's continuous. F is continuous. So the interval that we use is actually 3 to 5. F is continuous on the closed interval, 3 to 5, because it's differentiable, because f is differentiable everywhere. Now we are given that f derivative is controlled from 3 from below, controlled from above by 5. This actually also tells us that f derivative exists for every x. Okay, this also tells us that this function is differentiable, and differentiable implies continuous. So this also tells us that the function is continuous everywhere. Okay, so fx is continuous on the closed interval. Fx differentiable on the open interval 3 to 5. Differentiable on 3 to 5, so that we can apply mean value theorem. Then by mean value theorem, so this implies mean value theorem applies. Theorem applies for fx. So by mean value theorem, apply mean value theorem to fx. By mean value theorem, we apply mean value theorem, then we can get now the difference of two endpoints. f8 minus F2 is equal to F derivative at some number C times the difference of two endpoints. Sorry, 3 to 5. Oh, yeah. Sorry. The endpoints is actually 8 and 2. Sorry, 8 and 2. 8 and 2. 2 to 8. 2 to 8. Sorry. Okay, so 2 minus 8, we get a 6. So this is actually 6 F derivative C for some C. For some C in 8. 2 to 8. Okay, 2 to 8. Now we know F derivative C is bounded. F derivative X is bounded from 3 to 5 for all X. This implies F derivative C is bounded from 3 to 5. Now 6 F derivative C, multiply everything by 6. So 5 multiplied by 6, 3 multiplied by 6. So this means 6 derivative at C is bounded by 30 and 18. So this means, substitute by MeanValue theorem, then we get the difference F8 and F2 is bounded by 30 and 18. Then we are done. Okay. The idea of MeanValue theorem tells us that we can find the change of the function value by the derivative, the product of derivative, and the change of function value, change of input. Okay, more examples. Example. Show that the equation has exactly one real root. The equation has exactly one real root. Okay, now we show that it has one root. Okay, then we show that it has exactly one root. Okay, now so the first step, remember, so prove. The first step always is actually construct the function by the left side subtract the right side. So the right side is 0. So left side, we show the function equal to the left side. Okay, so first of all, we conclude that the function is continuous. Okay, so it's continuous. Then fx is continuous. Then the function that I defined is continuous because every term is continuous. Polynomial is continuous. Trig is continuous. It's continuous everywhere. Okay, continuous everywhere. Then we find 13 values such that the two endpoints has negative value. Okay, have negative signs. Okay, so for instance, if we choose F0, for instance, what is F0? F0 is you plug in 0. 2 times 0 minus 1 minus sine 0, which is 2 times 0 is 0, sine 0 is 0. So this actually we get a 0 minus 1 minus 0. Then we get negative 1. And then we pick 13 large value. So F1. So if you don't know which value you take a small value, you take a large value, then you can easily show actually one value is positive, one value is negative. But here we choose 0 and 1. 2 times 1 minus 1 minus sine 1, which will be 2 minus 1 minus sine 1, which will be 1 minus sine 1. Remember, sine value is bounded from above by 1. Actually, sine 1 is less than 1. So this actually 1 minus sine 1 is positive. And this, F0 is negative. So by continuity, then by intermediate value theorem, by IVT intermediate value theorem, there exists a number C a number x0 in 0 to 1 such that fx0 is the value 0, okay? i.e., if you plug in x0 to the equation, to the function, twice x0 minus 1 minus sine x0 is 0, i.e., x0 is a real root, okay? Is a real root to the given equation. Now this actually tells us that there is a root, okay? There is a root. Now, we actually show there can only be exactly one root, okay? Next, we show there exists exactly one root, one real root. Okay. Now we use contradiction, argue by contradiction. Suppose there are two roots. Suppose there are two roots. X0 and X1. So here X0 is different from X1. Okay, suppose without loss of general, then we can assume X0 is less than X1. So, okay, assume without the loss of generality, X0 is less than X1. Okay, then we can apply rule theorem. Then we have fx0 equals 0, fx1 equals 0. So we can conclude that fx0 equal to fx1. And this is actually condition 3. So this is condition 3. The two function values agree. Okay, this is condition 3 in rule theorem. Of rule theorem. Now 1 and 2 is automatically satisfied. Okay, satisfied. So condition 1 and 2 in rule theorem is satisfied by fx. Okay, because we check it. F is continuous. Y continuous. F is continuous on the interval, closed interval x0 to x1. 2, F is differentiable because it's differentiable everywhere. In particular, it's differentiable on the open interval x0 to x1. So we can conclude. So 3 is already done. Okay, the two function values at the endpoints x0 and x1, agree. They have the same function value. Okay, so we can conclude by rule theorem. Rule theorem tells us there exists a root. There exists a number c. In the open interval x0 to x1, such that f derivative at c, 1 is. Now remember f derivative. So remember fx is by definition 2x minus 1 minus sine x. And this take derivative, we get 2x, we get a 2, 1, we get a 0, sine x, we get a cosine x. So we get twice 2 subtract cosine x. Remember 2 cosine x is bounded from above by 1. So 2 subtract cosine x is always positive. Okay. So this means f derivative c is 2 subtract cosine of c is positive. But we know f derivative c vanishes by rule theorem. So then we get a contradiction. This is contradiction. Which is contradiction. So this contradiction shows that which shows that so this contradiction shows that which means so it's impossible. It is impossible that fx has more than two roots, two or more roots, two or more roots. But we know it has one root, so this means fx has exactly one root, one real root, more real root, exactly one real root. Then we are done. Then we are done. Okay, now let's go to next theorem. This theorem tells us that if f derivative vanishes, then actually f is constant on a connected interval. So if f derivative vanishes, we know for x in an interval a to b. A to b. Then fx continuous. Fx is continuous on a to b. Sorry, f is a constant on a to b. Okay. Okay. Now from differentiation rules, we know if a function is constant, then its derivative vanishes. Okay. Constant derivative is 0. Now, conversely, if f derivative is 0, now can we conclude that actually fx is constant? This actually very there's some subtlety here. There's some subtlety here. So you should be really careful. Here, this is only true if we are talking about one connected interval, okay, a to b, then it's true, okay, as long as it's connected interval a to b, it's true. Now, in general, it can be wrong. So it should be really careful. So for instance, if we have more intervals, for instance, we have a bunch of intervals. So for instance, we can study the floor function. Remember the floor function? Now it's actually locally constant. Now for each interval, it's constant, but globally it's not. Globally it's not. So it's locally. The key thing is it's locally constant. Now if you take derivative, and when we take derivative, we only use local information. So its derivative vanishes everywhere, but globally it's not a constant. It's only locally constant, but not globally. Be careful. So if we have more intervals which is not connected, then it can be wrong. The function can fail to be globally constant. Okay, the floor function is such an example. So for connected interval, the key thing is we can apply mean value theorem. Okay, probe. Now we check that the function actually satisfies the mean value theorem. So that mean value theorem applies. So we know f derivative exists is actually 0 for all x values. Okay. Now, so pick two numbers, x1, x2 in a to b. So the idea is, so this is a, this is b, ab. Okay, so we take 2 points, x1, x2. Okay, then we check, then fx, then we check fx is continuous on closed interval x1 to x2. 2, fx is differentiable. Differentiable on open interval x1 to x2 because it's actually differentiable on a larger interval a to b. So in particular, it's differentiable on x1 to x2. Then we can conclude by mean-value theorem. Mean-value theorem. fx2 summation fxy equal to f derivative at c x2 summation xy by mean-value theorem. Now remember f derivative c for some c in some number c in the interval x1 to x2. Now x1, x2 lies in between a to b. So we know, so f derivative 1 is for all x in a to b. This implies, in particular, c lies in x1 to x2. So c actually lies in between a to b. Okay, so some number c here. Okay, so which implies f derivative at c should be 0 because c lies in a to b. Okay, so this means by mean-value theorem, then we can get this condition. We plug into the equation, plug into the given equation. Okay, so that we can conclude fx2 minus fxy is 0 times x2 minus xy, which is of course 0. So this means fx2 equal to fxy. Now we pick any arbitrary x1, x2 in the interval a to b, then we get the same function value. Okay, now if you take any value x3, then you can get f1, x2 equal to f3. Now you can take any arbitrary value x3. So this actually tells us that the function is actually constant since x1 and x2 are arbitrary. Then we can conclude. Then we see that f is a constant. Fx is constant. It's constant on a to b. Okay, then we're done. Okay, another corollary is if two functions have the same derivative. Corollary. Okay, corollary. If f derivative x equals g derivative x for all x in a to b, then they differ by a constant. I.e., if two functions have the same derivative on a connected interval, okay? Connected interval, okay? Be careful. Now, in general, it can be wrong. It should be connected interval. Connected interval. Okay, so then f derivative, then fx equal to gx plus constant c. Okay, they differ only to a constant. Okay, i.e., if we know two functions have the same derivative, then actually the function differ by a constant on a connected interval. Okay, on a connected interval. Okay, proof. Let's capital F be little f subject gx. Then capital F derivative. Now we distribute the differentiation. So distribution property, f derivative subject g derivative. Now f derivative equal to g derivative, so their difference is 0. So we can conclude. Okay, so we can conclude from our last theorem a function has zero derivative for x in a to b. The function has zero derivative on a connected interval a to b. Then we can conclude this implies fx should be a constant. Okay, fx is constant. Okay, so this means fx little f minus little g should be a constant c. Now, if you move g to the other side, then this means fx is gx plus constant c. I.e., they differ only by a constant. They differ by only a constant. Okay, example. Let's see some example. Show that arc sine x plus arc cosine x is actually pi over 2. Pi over 2. Okay, prove. Okay. First, we take derivative. Now, remember, let fx be arc sine plus arc cosine. Now we differentiate. Remember arc sine derivative. We did this. Arc sine derivative. What is arc sine derivative? And arc cosine derivative. What is arc sine derivative? Arc sine derivative is y over square root of y minus x squared. Okay, how do we get arc cosine? In this case, we apply co. Okay, we apply co. Once we apply co, then we get negative y. Okay, so we get this negative y over square root of y minus x squared. So if we differentiate f derivative, then we get arc sine derivative plus arc cosine derivative by differentiation property distribution. Okay, arc sine derivative, you get a y over square root of y minus x squared. Arc cosine, we get a negative y over square root of y minus x squared. Now this actually we get easily, this is actually 0. So for all x, so here for all x, now it's defined, it's differentiable from negative 1 to 1, negative 1 to 1. Okay, negative 1 to 1. So we can conclude, so this means fx is constant. Is constant. Negative 1 to 1. So for instance, we plug in 0. So f is constant. So plug in. So f0, in particular, f0 is arc sine 0 plus arc cosine 0. Now we know sine 0 is 0, so arc sine 0 is actually 0. Now we know cosine pi over 2 is 0, so pi over 2 equal to arc cosine 0. We take arc cosine. Okay, so this we get actually this is 0 plus pi over 2, we get pi over 2. So the function is constant from negative 1 to 1, open interval. Its value is pi over 2. Now we also need to check the two endpoints. F1, what is F1? Arc sine of y plus arc cosine of y. We know sine pi over 2 is actually y. Take arc sine, so we get a pi over 2 is arc sine of y. Okay, we get an arc sine of y. We know cosine 0 is y. So we know 0 equal to arc cosine of y. So this is actually pi over 2 plus 0. Then we get again pi over 2. Similarly, f negative y. Then we get this is actually arc negative y plus arc cosine negative y. Remember, cosine pi is negative y. So we get a pi is actually arc cosine negative y. What is, sine negative pi over 2 is negative y. So we get arc sine, so we get negative pi over 2 negative power 2 is arcsine negative 1. So this is actually negative power 2 plus power 2. Oh, sorry, plus pi. Arc cosine is negative 1 is pi. So again, we get power 2. And then we again check the two endpoints. So this shows that fx equals constant power 2 for all x in negative 1 to 1. i.e., arcsine x plus cosine x is actually power 2. Okay. Similarly, we also have this another example. You can also check this by yourself. Fx. So for instance, example arctangent x plus arccotangent. The same thing. We get actually this is power 2. You can check. The same idea. So prove. How do we prove it? So we again let fx be arctangent plus arccotangent. Okay, remember arctangent derivative. Arctangent x derivative is, we did this. Check your notes. Arctangent derivative 1 over 1 plus x squared. Arccotangent. Remember, once we have a co, we have negative 1. So we apply the thing by negative 1. Okay. So f derivative will be, we distribute the differentiation. Then we get this is actually 1 plus x 1 over x squared. Arccotangent derivative we get negative 1 over 1 plus x squared. So the difference is actually 0. Okay, the difference is 0. So we get f is actually constant. Fx is constant. Now, to find the constant, you find, for instance, you plug in f negative f1 arctangent of y plus arccotangent of y. Now, remember tangent power 4 is 1. Cotangent power 4, 45 degree is 1. So then you get take arctangent. Arctangent is actually power 4. Arccotangent 1 is actually power 4. Then you get power 4 plus power 4. You get a pi over 2. Okay. So this actually we get arctangent x plus arccotangent x is again pi over 2. Okay. All right. Example. Show that square root 1 plus x is computed from above by 1 plus half x for all x greater than 0. Okay, what we do is we use mean value theorem. Prove. Okay. Okay, we consider this. So let's fx be be this 1 plus the right side minus the left side. Okay. Now, for x is positive, for x greater or equal than 0, f is differentiable, is continuous, and differentiable everywhere. So that we can apply mean value theorem. Okay, mean value theorem. Now, what is f0? f0 is plug in 0 minus. So this is the y half times 0 is 0 minus square root of y minus square root of 1, which is 0. Okay, then we can apply mean value theorem. Mean value theorem says take the interval from, for instance, 0 to x, for instance x0. Okay, now f x0 minus f0 is equal to f derivative at some number c, x0 minus 0. So here x0 is positive, so which will be f derivative at c times x0. Remember, x0 is 0, f0 is 0, so x0 is a thing. Okay, for some c in 0 to x0, so i.e. c is positive. So here c is positive. Now f derivative, we check the derivative. fx is 1 plus 1 half x minus square root 1 plus x. So f derivative, we take derivative. F derivative x. 1 derivative 0, 1 half x derivative is 1 half. Now the square root, we need to use, chain rule. Square root of 1 plus x equal to 1 plus x to the 1 half power. Use chain rule and power rule. So that we get a 1 half here, then 1 plus x here. We get this, okay? So this is the 1 half minus 1 half times 1 over the thing. So if you factor out this 1 half, so it's 1 half, 1 minus the thing. First of all, for x greater than 0, if x greater than 0, then we have this thing is greater than square root of y, which is y. So the denominator is greater than y. So this means 1 over square root of x, 1 over square root of 1 plus x is bounded by y. Okay, bounded by y. So this means y minus the thing is positive. Okay. So this means f derivative of x is positive for x greater than 0. Okay. Remember our value of c. Our value of c is c is positive. Okay. C is positive. C is in 0 to x0. So c is positive. So here, let's label this by equation. Let's use equation 1 and equation star. Okay. From equation star, we know. So let's just write equation star. F0 is f derivative at c times x0. Now x0 is positive. Okay, f derivative of c is positive because c is positive, and the derivative is positive when its input is 0. The input is positive. Okay, so we can conclude that this is actually positive times positive. Then we get a positive number. So then we get f x0 is positive. Okay. Now remember, so x0 is arbitrary. So this means fx is positive for all x greater than 0. Since x0 is arbitrary, it's arbitrary positive number. Okay, i.e. 1 plus 1 half x, subtract 1 plus x, subtract square root of 1 minus 1 plus x is greater or equal than 0. So if you move terms around, then you get square root 1 plus x is bounded from above by 1 plus half x for all x greater than 0. Then we are done. Okay. Okay, this problem. Okay. All right. Now let's talk about the next section. Next section. How derivative. So next section, 3.3. How derivatives affect the shape of a function. How derivatives. Okay, how derivatives affect the shape of a graph. Okay. One of the key things that in calculus is we want, given a function, we want to find its derivative, okay, and a higher derivative. Now, conversely, if we are given derivative or higher derivative, what can we see? What can we tell about the original function f? So, so the question is, what does f prime tells us? What does this f prime tells us about the function f? Question. Okay. Okay. Now remember, f derivative. The derivative tells us the change of the function. Okay, the change rate of the function. Now, if the change rate is positive, then this tells us that the function is actually increasing. Okay, change rate. Think of the change rate. If the change rate is negative, then the function is actually decreasing. Okay, then the function is actually decreasing. Then we get the first increasing decreasing test. First increasing decreasing test. Increasing decreasing test. Which says this: if a function is positive, it's derivative. If f derivative is positive for all x, in an interval for all x in an interval I, then fx is increasing. F is increasing on I. Okay, fx increasing on I. B, if derivative is negative for all x in an interval I, then fx is actually decreasing. Decreasing on I. Okay. Okay. Now let's prove. Now let's prove. Okay. So suppose we have 2 points, x1, x2. Now if we take 2 points x1, x2 from A to B. Then we have fx2 subset fx1 by MeanValue theorem. By MeanValue theorem, we check by MeanValue theorem. By MeanValue theorem, we have f derivative at c x2 minus x1. So here you need to check that the MeanValue theorem applies here, because here the derivative exists everywhere, so it's differentiable. So differentiable implies continuous. Then the function is satisfies 1 and 2 in condition 1 and 2 in MeanValue theorem. So we can apply MeanValue theorem. Okay, now if so here remember x2 is bigger than x1, so which means x2 is subset x1 is positive. If f derivative c is positive for all x in I, then we know c is in I, c in I for some c in I, for some c in between x1 to x2. So this implies f derivative c is actually positive. So f derivative c is positive, multiply the positive factor x2 minus x1. So this is actually positive times positive. So it's, positive times positive is positive. Product of two positive factors is again positive. So this implies fx2 minus fx1 is positive, which means f2 is bigger than x, the function value at x1. Okay, i.e., if the input is bigger, the function value is also bigger. So this implies, i.e., since x1 and x2 are arbitrary, then we see, we conclude that fx is increasing. Fx is increasing on I, i.e., bigger input gives us bigger function value. Okay, bigger function value. Now, if so, this actually this proves part A. Okay. Now, if f derivative of x is less than 0 for all x in I, then f derivative c is of course less than 0, because since c lies in I also. So f derivative c is negative number, multiply a positive number is again negative. Okay, so this is negative times positive is again negative. Okay, so f derivative is, so this implies fx2 subset fxy is less than 0. So this implies fx2 is less than fxy, i.e., bigger input gives us smaller output. So this implies fx is decreasing on I, strictly decreasing actually, decreasing on I. Okay, because it's arbitrary x1, x2. Okay. All right. Example. Okay. Now, this fx is x cubed minus 3x squared minus 9x plus 4. Find what this function is, what interval the function is increasing or decreasing. Find the increasing, decreasing, find the interval of decreasing, interval of increasing. Find the intervals of increase or decrease. Okay. By increasing decreasing test, it suffices to find on what interval that the derivative is positive, what interval the function derivative is negative. Okay. All right. So first we take derivative. Okay. Derivative f derivative is 3x power x power 2 squared power rule. Now 6, then subtract 6x minus minus 9. Now if you factor out 3, so this will be 3x squared minus 2x minus 3. And then you find this is 3x minus 3x plus 1. Okay, factor is quadratic. And you find what interval is positive and negative. So it has 2 roots. So this derivative is degree 2. Degree 2. It has 2 roots. And 2 roots. 2 roots. 3 and negative 1. Now its coefficient is 3, is positive. So it's concave up. Okay, concave up. So it actually looks like this. Negative 1, 1, 2, 3. So it looks like this manner. Looks like this manner. This is 3. This point is 3. This point is negative 1. So you check x, y value. So you see f derivative x is actually positive, equivalent to x less than negative 1 and x greater than 3. X greater than 3. F derivative is negative, which is equivalent to x from negative 1 to 3. Okay, negative 1 to 3. Now, if you don't know how to plot its graph of this quadratic, you can also find, talk about the intervals, the roots, the 2 roots, partition the x-axis into 3 intervals. Okay, you can also use this manner. It is negative 3, negative infinity to negative 1. Then negative 1 to 3, 3 to infinity. And you plot the table. X minus 3, x plus 1. F prime x is their product. So you use this table. You find on this interval it's negative. It's negative is positive. This is negative. This is the positive. This is the positive. So their product, this is positive, negative, positive. Okay. So you can also use this manner to find when it's positive and negative. Okay. So the function, the derivative is positive from negative infinity to negative 1 and 3 to positive infinity, these 2 intervals. Okay. So we can conclude that by increasing decreasing test, f derivative, so f, we add another rule. So fx, by increasing decreasing test, derivative is positive, it means the function is increasing. Derivative is negative, it means the function is decreasing. So by increasing decreasing test, f increases on negative infinity to negative 1 and 3 to positive infinity. F decreases on negative 1 to 3. Okay. Okay. Now you see, if we plot a rough graph of f of increasing decreasing, just increasing decreasing property, then we can conclude how it looks like. Now, if you plot a graph, negative 1, 3, a rough graph, just a rough graph. Now it's decreasing on negative infinity to, it's increasing from negative infinity to -1. So it's increasing. So suppose it's increasing. Now decreasing from -1 to 3. Decreasing from 1 to 3. Now, and again, increasing from 3 to infinity. From 3 to infinity. 3 to infinity. You see, we have, so what happened at the -1? -3. So -1 and 3. You see, at -1, at x equals -1, the function left side is increasing, the right side is decreasing, so it's increasing, then decreasing. Then we have the function fx attains a local maximum and x equals 3. At x equals 3, fx attains a local minimum. A local minimum. Okay, so you see, if a function increases and then decreases, then we have a local max. If a function decreases and then increases, then we have a local min. Okay, then we have a local min. So from this property, we can actually find local minimum, local maximum of a function. Local maximum and local minimum of a function. Okay, so this is actually called the first derivative test. The first derivative test. The first derivative test. Let's use capital F. The first derivative test. Test. Okay, now suppose we have a critical number. We have a critical number. Now, by continuity, if the function change, the derivative change sign, if the derivative is continuous, then actually we know the derivative should vanish. Okay, if the derivative is not continuous, then actually we know at that point the derivative does not exist. So we actually conclude that at C is actually critical number. We look for critical numbers. So suppose that C is critical number. Critical number of a continuous function. Fx. Now, if f derivative changes its sign from positive to negative, let's see. Then now positive means it's increasing, negative derivative means it's decreasing. So the function increases and then decreases. Then we have, then fx attains a local max. Okay, increase and then decrease. Then we have a local max at x equals c. Now if f derivative changes from negative to positive at c, then the function decreases, then increases. Okay, then fx attains a local min, attains a local minimum at c, x equals c. Okay, now suppose does not change sign. Suppose part C, if the derivative does not change sign, changes sign at x equals c, then we can conclude that fx has no maximum or no minimum. no maximum or minimum at x equals c. Okay, now for example, fx equals sine x equals sine x. Now its graph looks like this if you plot the sine x graph. Okay, now this is actually pi over 2. This is 3 pi over 2. This is pi. Okay, now you check that f derivative x is actually cosine x. Cosine x, you see from 0 to pi over 2, cosine x is positive. Okay, f derivative x is positive. Cosine x is positive, greater than 0 for x in 0 to pi over 2. This implies f is increasing. So sine x is increasing on 0 to pi over 2. Okay, now cosine x is less than 0 for x in pi over 2 to 3 pi over 2. Okay, second and third quadrant. So actually we can conclude that the sine x is decreasing. So fx, so this means by increasing decreasing test, sine x is decreasing. It's decreasing. Pi over 2 to 3 pi over 2. You check from the graph. Actually, from pi over 2, the function value achieves the maximum at 1. Now from negative 3 pi over 2, this minimum is -1. Okay. Now you see, when x is pi over 2, cosine x changes from, so cosine x changes its sign, changes from plus to minus at x equals pi over 2. Okay. Left side is acute angle, cosine value is positive. Then greater than pi over 2, then it's obtuse angle in the second quadrant, then the cosine value is negative. So cosine value changes from positive to negative. Cosine is derivative of sine. So actually we see, this is exactly what we see from the graph. So sine x attains local max at pi over 2, at x equals pi over 2. And the local max is, of course, sine pi over 2 is actually equals 1. Okay, equals to 1. Okay, more examples. Fx equals x squared. Okay, its graph, square function is graph. It looks like this manner. If you plot it in smooth manner, so this is y equal x squared. This is x, this is y. Okay. Now you see, f derivative is 2x. Now, if x is increasing, if x is positive, then f derivative x is twice x is also positive. Then this by increasing decreasing test, f derivative is positive, then fx is increasing. Now you see, from 0 to infinity, the graph is actually indeed increasing. Now if x is negative, then f derivative is 2x is less than 0. Then fx decreasing. Now at x equals 0, okay, we have a critical number. The derivative vanishes. The derivative 2x vanishes when x is 0. Now f derivative of x changes its sign, changes from negative to positive. Okay, to positive. Okay, so this means This means fx by the first derivative test changes from negative to positive. Then we can conclude that the function actually achieves a local minimum. Then fx attains a local, this is also of course global, a local minimum at x equals 0. Okay. Now more example. Fx equals x cubed. Now x cubed, if you plot its graph, it looks like in what does it looks like? Okay. We may continue next time about x cubed. Y equals x cubed. Right now it's already over time. Okay, let me stop here. And any questions? Any questions? Okay, let me stop here and continue on Wednesday.